official start. And today we have a pleasure to have Dr. Renata Modzelewska-Łagodzin from the, I memorize that, Siedlcach University of Natural Sciences and Humanities. That's what the internet says, the official name of the university she's employed in. Her specialty is astronomy, but really very nearby astronomy, cosmic rays close to the Earth. And the actual reason why we got in touch is that we both participated in FNP program, mentoring program, which is aimed to help younger people to develop better and more efficiently their careers. So I try to help her. Anyway, the topic of the seminar is heliospheric modulation of cosmic rays.
Good morning, thank you. I will talk about heliospheric modulation of cosmic rays, experiment and modeling. There is the plan first. The plan of my talk is a few words about cosmic rays and about environment where cosmic rays are modulated. This is near the sun. About the sunward about experiment based on monitor measurements.
Could you speak louder? People in the back.
Yes, I try.
Yes.
Especially some of that.
The next part is theoretical modeling based on particle transport equation. And we apply two different approaches, deterministic and stochastic approach to the numerical solution. And we start from Fokker-Planck equation and corresponding set of stochastic differential equations. We apply some numerical methods for solution, and I will show some results. So, shortly, cosmic rays are high energy particles, most protons, about 90%, 10% alpha particles, and about 1% other nuclei. This is the composition. And here you can see typical proton spectra of cosmic rays. This is differential intensity or flux of cosmic rays versus a wide energy interval up to 10 to 21 electron volt. Here we can see narrow interval of energy. Here we can see low energy solar cosmic rays. This is this part of spectrum, and galactic cosmic rays. This is this part, and galactic cosmic rays depending on solar activity. For minimum of solar activity, for minimum number of sunspots, and for maximum of solar activity. In this figure we have also designates domains of different measurements. A low part of cosmic rays measured by spacecrafts, higher cosmic rays measured by stratospheric balloons, and higher energy measured by neutron monitor and meson telescopes. Our study concentrates on these measurements and on heliospheric modulation of galactic cosmic rays, and we concentrate on neutron monitor measurements, on ground-based neutron monitor measurements. A few words about environment. Solar wind. Solar wind is the constantly expanding solar corona, solar atmosphere, and solar wind is supersonic, and average speed of solar wind varies from
Is supersonic with respect to the speed of sound where?
in the interplanetary space, in the heliosphere. Solar wind speed varies from 400 to 800 km per second, and the Ulysses mission shows different pattern of solar wind speed depending on solar activity. Here we have low solar activity, solar minimum, very low number of sunspots on the photosphere. We have the maximum of solar activity, we have more or less symmetric distribution of solar wind speed. Solar wind is high conductive plasma with frozen in heliospheric magnetic field. And due to the sun rotation, magnetic field lines are formed into Archimedean spiral or Parker spiral. Parker is the author of this theory of solar wind. And cosmic rays coming from galaxy undergoing the influence of heliospheric magnetic field. Here we have art view of heliosphere. Heliosphere is the space around the sun. The radius of the heliosphere is about 100 astronomical units. And boundary of the heliosphere is the termination shock. The termination shock is the region when solar wind becomes subsonic. After we have heliosheath, the region between termination shock and heliopause is the heliosheath, and heliopause is the outer boundary, and here we have interstellar space. A few words about Voyager. Voyager are mission which explores distant regions from the sun. Voyager 1 crossed the heliopause in 2012 and now explores interstellar space. And current position of Voyager 1 is about 133 astronomical units from the sun. Voyager 2 now is in the heliosheath in this region, and current position is about 110 astronomical units from the sun.
So this picture is not the
Yes,
right
this is
scale.
not-
It's
This
not
is
the
not
scale,
actual.
because the Earth orbit is 1 astronomical unit, and it's certainly not 100 such orbits
Yes,
here.
yes,
So
it's
this
art
must be
view.
a logarithmic scale.
Yes, this is art view, and so for general very famous phenomena is the solar cycle. Solar activity changes with 11 years. Here we have number, the main indicator of solar activity is the number of sunspots on the photosphere, and in the minimum epoch of solar activity we have a low number of sunspots. In the maximum epoch of solar activity we have high number of sunspots. In the bottom figure we have cosmic ray intensity measured by neutron monitor in Greenland since 1955 up to now, and we can see a very good anti-correlation between the solar activity and the cosmic ray intensity. This is very clear long period changes of cosmic ray intensity.
Clearly, the total intensity of this solar activity fluctuates,
Yes.
and so does probably a period. Has it been studied? What sort of statistics does it obey? Is it Gaussian distributed, or is it?
We will try.
Or there are too few data points, or what?
We will wish that it will be Gaussian, but in some cases it is not Gaussian, unfortunately. And the theory.
Why, unfortunately? Then there
Because
must be a reason.
Yes, but the investigation is not so easy in that cases. In that fluctuation is non-Gaussian.
Yeah, here it seems that lower activities are longer, but I'm not sure if it is statistically supported.
Generally, in the solar maximum, we have very much disturbances on the sun, and they are non-Gaussian, I think. But in the minimum epoch,
Are these data about the activity available for other
Yes,
early
yes,
periods?
yes. Solar activity is measured since 17th century.
17th century.
Yes, yes. Cosmic rays by neutron monitors are measured since 1955. In 1950s, Simpson proposed this kind of measurement of cosmic rays, but in the past we can measure cosmic rays by, for example, carbon-14 and so on. Solar cycle is the half of full.
What is this, the source of these neutrons? Neutrons are not.
Later,
Living.
I will talk about.
You will talk about neutrons because they don't
Yes.
live long enough to
Yes.
to reach Earth.
Solar cycle is half of full solar magnetic cycle. Solar magnetic cycle takes 22 years. In one minimum, when magnetic field lines are directed away from North Pole and directed towards South Pole, we call it positive polarity. In the maximum epoch, we have mixture situation of polarization, and in the next minimum, we have vice versa polarity when magnetic field lines are coming toward North and outward from South Pole. We call it negative polarity. Solar cycle and solar magnetic cycle is caused by action of solar dynamo. And here we can see how it works shortly. We have in solar minimum poloidal field, which is transformed in time from poloidal to the toroidal because of differential rotation of the Sun. Equatorial region rotates with a period 27 days, and the polar region rotates much slower with a period about 40 days. And due to this transformation, we have in the maximum of solar activity very mixture situation and dominate toroidal peak. And next, from maximum to minimum, we have transformation to the poloidal field with vice versa polarization. And details of this dynamo I will send to proper references. And about cosmic ray shower. Here we can see a cascade of secondary cosmic rays in the atmosphere caused by primary proton. And we have three components: a soft component, neon component, and nucleon component. Stars designates nuclear collision in the atmosphere and ovals decay processes. So in this process we have neutrons which are coming to the ground and are measured by neutron monitors. Neutron monitors measure mostly thermal neutron. They are slower by some kind of a moderator in the detector, some kind of paraffin or plastic. And next they are multiplier by, for example, plumbum. From one neutron we obtain 10 neutrons for statistics, for better statistics, and we register these thermal neutrons. Here we can see different kind of detectors, spacecrafts at the top of the atmosphere, balloons in the atmosphere, and ground-based detectors, meson telescopes and neutron monitors, which we concentrate on this kind of detectors. Here we can see a map of neutron monitors around the world. We have about 40 stations around the world. They are operated since 1955, more or less. Up I can show you some cosmic ray variation observed by neutron monitors in different scales. Here we can see very clear 11-year variation of cosmic ray intensity. This is connected with the solar cycle. And we also can see 22 years solar magnetic cycle dependence with peak and plateau shape. Peak we can see in negative polarity and plateau shape in positive polarity.
So there's some asymmetry between north and south.
Yes. For example, between them, this is the highest level of cosmic rays ever measured in this minimum 2007-2009. In this period, solar activity was very low.
But this must be a highly directional event, because if you are looking not in the direction of the sun but in the opposite direction, there should be no influence of the sun on these cosmic rays.
Yes, I think this is not so much asymmetry in this view because we have average situation, average modulation in this region of the sun.
But this is looking in the direction of the sun.
Yes.
No, those are not cosmic rays coming from the sun. She's measuring galactic cosmic
I
rays.
understand, but if the galactic cosmic rays have a period of 11 years, that means that this is influenced by the sun.
Yes. I talk about heliospheric modulation.
That's
This
right.
is the modulation caused by sun and solar.
Yes,
Sure.
And my question is, does one see this modulation looking in the opposite
Yes.
direction of the sun?
If we observe Earth is rotating and it looks different.
So this is
directions.
average.
This is the average one. Yes. And if we see on a short time scale, for example, this minimum, very special, we can see periodicity of cosmic rays with a period of 27 days. This is 27 days. 27 days. This is 2007-2008 from this time period, and we have few months, and this variation of cosmic rays we think is connected with solar rotation. Solar rotates with a period of 27 days. Here we can see cosmic ray intensity measured by Moscow neutron monitor, and we can see other parameters measured near Earth, solar wind speed, and heliospheric magnetic field components, and they also have a similar variability. Also 27 days. If we look carefully on a shorter time scale, we can see some kind of decrease of cosmic ray intensity. We call it Forbush decrease. This phenomena is caused by disturbances in the interplanetary space caused by, for example, shocks and coronal mass ejecta coming from the sun. If we look on the shortest time scale, this is about one month. I remind you that this is 27 days variation. If we look on the shortest time scale, this is 1 month. In September-October 2007, we can see very clear 24 hours variation. We call it solar anisotropy. This variation is caused due to the Earth
Rotation of the Earth.
Yes. Yes.
Okay, that is the answer to my question.
This is the mechanism of solar anisotropy. This mechanism was proposed by Krymski and Parker, and a solar anisotropy vector is the equilibrium state between inward diffusion of cosmic rays along magnetic field line and outward convection by the solar wind, and as a consequence we can see stream of cosmic rays directed this direction, and we call this vector oppositely directed solar anisotropy. And the Earth rotates, and we can see 24-hour variation of cosmic ray intensity. We call it solar anisotropy. This is the example of 24 hours intensity measured by Moscow Neutron Monitor in January 2007. Concerning the cosmic ray anisotropy, we have two possibilities. We could take harmonic analysis or Fourier transform for individual neutron monitor and obtain two-dimensional cosmic ray anisotropy AR and A5. AR is the component directed to the Sun, and A5 perpendicular. If we take global spectrographic method, we can use data from neutron monitor network, about 40 stations around the world, and in this case we can obtain 3D anisotropy and also hourly. In this case daily anisotropy, and in this case hourly. That the resolution is very good. If we write diffusion convection equation, this is the diffusion and convection part, and if we obtain successfully these components from measurement, we can calculate different modulation parameters. For example, diffusion coefficients, density gradients, and the ratio of the diffusion coefficients. And in this equation, plus and minus corresponds to different sectors of the interplanetary magnetic field. K is the diffusion coefficient, G are gradients, and U is the solar mean speed, V is the cosmic ray particle speed, and C is the Compton getting factor.
In what sense this is a set of equations that looks like definitions of A, R, A theta, and A5?
Yes,
Because
I call it equation because I try to solve this.
how can you solve this equation if A does not appear on the right-hand side?
It's already solved.
Now, we from observation,
Yeah,
we
these are
observe
known.
these components. These are known.
Sure.
Okay.
We obtain.
So what are you looking for then? What are you solving this for?
This is solved for G, for coefficient G.
Yeah, okay.
For G, for K, for diffusion coefficients, and for
Okay.
gradients.
Okay.
I solved it.
So A is observation, and the
Yes.
right-hand side is
Yes,
theory.
this is observations, and these are parameters which we
Which you want to
calculate from
determine, yes?
observation. Yes, exactly. Recently published results of estimation these parameters, which we are talking about. 1 month ago, we have this paper with collaboration with Professor Aluvalia, and in this paper we calculate diffusion coefficients, mean free path of cosmic ray particles, and radial and latitudinal gradients. The parameters are for Earth orbit.
Could you go back to, so we understand, what is being varied? Psi is,
Psi is the angle between cosmic ray, between heliospheric magnetic field and radial direction in the equatorial plane, and this is this
so
angle.
because there are
This is
many
this
more
angle.
coefficients.
This is this angle.
Okay, but there are many more coefficients on the right-hand side. You have 3 values of A. Now on the right-hand side you have
Yes.
K,
we
you have G, many coefficients. So how
yes.
can you determine them?
We make some assumptions. We simplify this equation because we have no possibility to obtain in a general case.
So no, in what sense this equation is being solved for
This is the more general, and if we, for example, average for a long time, we average the different sectors.
Yeah, this is already average because there's no time here, so this is some kind of an average.
Yes, I think this equation is general, but if we, I can show you our
And
paper.
how many unknowns do
Yes,
you
that
have?
is my question. You have K,
If we average over azimuth, so if we have data for example, long period,
yes. You
we
get rid of these
yes.
terms, okay.
we have only two gradients, gr and d theta,
And K,
and
K,
k. Yes,
so still you have more than,
yes. We perform many assumptions. I will show you our paper.
no,
About that.
I
The
want
paper
to
is to
that would
20
not.
pages, and it is not so easy.
What
So in other words, you add some additional assumptions.
Yes.
So it's not just these three equations,
Yes, yes.
but there's
We-
something, some
yes.
additional knowledge which is
Yes,
required
yes.
to determine
This
this
is,
concept.
this is the more general, but in our calculations we simplify because we have no possibility to solve this kind of general equation. This is this publication. If I have time, I will talk about this publication. And then the next part of my talk is the mathematical modeling by Parker transport equation. This is the very famous equation. This is diffusion equation. In this equation, function phi is omnidirectional distribution function depending on radial distance, heliolatitude, and heliolongitude. This function depends also on magnetic rigidity of cosmic ray particle and is time dependent. In this equation, U is solar velocity, Vd is the drift velocity in the heliospheric magnetic field, and Kg is the symmetric part of diffusion tensor of cosmic rays. The first part of this equation is the diffusion.
So
This is the convection and the drift.
But the components Ij must be somehow
Tak,
summed
this is-
over.
Yes, this is the diffusion convection approximation.
But Kij is a matrix.
Yes, this is the matrix.
So how come F does not depend on the coefficients Ij? There must be some kind of summation over Ij. Is the gradient component?
Yes, this is the symbolic vector. This is the gradient.
No, I
This is
don't.
the divergence.
No.
But still
I don't understand the
Kaj
notation.
appears.
Kj is,
What
this is the,
what do these dots mean?
This is the tensor product.
So in other words, the gradient has this additional indices, yes? Index.
Yes.
Index. So it's not
So
a
I would
gradient.
put
Yes.
J and I under this
But this
gradient.
is
This is
the
a-
derivative in the J direction, and this is the derivative with the I
Yes,
direction.
this is in spherical coordinate system. R theta p. This is the product of matrix K
Yes.
With the vector.
with vector. Yes.
So the vector should not have an arrow because it's not a vector but the component in the
Yes.
J
This
direction.
is component.
In other words, there should be
Yeah.
J and I underneath, under the numbers.
Yeah. Okay.
Yes. Yes. And it must be
This
J.
should have I
Yes.
component and this is J
Yes. Yes.
component.
Yes. This is my mistake. Yes. Yes. This equation is four-dimensional three spatial coordinates, magnetic rigidity of cosmic rays and time is the second of the parabolic type equation, and it is worth to underline that if we assume the first time derivative equals 0, this equation remains freely parabolic type with respect to magnetic rigidity. And if we assume this derivatives equals 0 depend on magnetic rigidity, this equation also remains a parabolic type with respect to time. This equation unfortunately is not solved by analytical way, so we employ numerical methods.
What about U, capital U? Does this depend on R?
Capital
What is this?
general no, because in the heliosphere solar wind velocity versus distance is quite stable and is constant.
What about K? Does this depend on R?
Yes, diffusion coefficient depends on distance, on magnetic rigidity, and on time also.
So where does it, how do you know Ki?
I will show. The first method we can use is the final difference method. We transform this equation to the set of linear equations and solve these linear equations by Gauss iteration.
No, they are linear, but the coefficients depend on the...
Yes, but the equation is linear because
No, I understand that it's linear, but the coefficients are not constant.
yes, coefficients
That's
are in this form. Coefficients of the equation are in this form. Here we have diffusion coefficients, solar wind speed, and drift velocity. And the diffusion coefficients is the sum of symmetric and antisymmetric part. And the diffusion coefficient is in this form. And drift velocity is taken from this old paper as this one. And C is the angle between magnetic field line and radial direction in equatorial plane. Delta is the angle between magnetic field line and radial direction in the meridional plane. And beta is coefficient or is the ratio of perpendicular to parallel diffusion coefficient. And beta 1 is the ratio of drift diffusion coefficients to parallel diffusion coefficient.
And where does this come from? What is the physical background that enables one to find this?
If you write the diffusion tensor in the reference frame connected with solar wind, with magnetic field, the diffusion tensor is very simple.
And then this is transformed
Yes,
to
this is,
frame.
and if we have, if we want to solve this equation in a heliocentric coordinate system, we could transform. So it is some kind of rotation in the space, and we obtain this kind of very complex diffusion coefficient.
Because of the rotation?
Yes, because of the rotation.
So
From one,
these are like Euler angles or something?
yes, this is some kind two rotations, and we have diffusion tensor in heliocentric coordinate system.
So would it not be simpler to solve it in the system where the equations are simple?
I don't try.
And then transform the result?
Maybe. I don't try, but I have heard from my professor that it would be very difficult to solve in test.
Why, if the
I don't know.
one usually chooses the coordinate system,
Maybe I
in
try.
which the solution is the simplest?
Yes, yes.
And then you
Maybe
can
the
transform.
transformation is. I don't
The
know.
transformation, if this is going to a rotation
This is not
rotation
so.
system, so
This is
this
easy.
should not be complicated.
Yes. Yes. Yes.
So you've got this complicated set of differential equations, and then you replace them by algebraic by taking finite difference.
Yes.
That's I understand. But what are the boundary conditions?
Oh, the next slide. The boundary conditions. We assume no modulation after the termination shock. We assume the boundary of heliosphere 100 astronomical units. This is normalization intensity equals 1. No modulation for maximum energy equals 100 GeV. And we assume reflecting inner boundary. So we assume that this differential intensity does not change near the sun. And we also assume periodical character versus heliolatitude and heliolongitude. And if we solve this equation, non-stationary equation, we assume that the stationary solution is the initial condition for non-stationary solution. And here we have stationary solution, and we solve this in time. And this is another energy. First we obtain a stationary solution for this energy, and this is the initial condition for non-stationary case. And some results. This is the paper published last year. We tried to model 11-year variation of cosmic ray intensity since 1996 up to 2012, and we assume this kind of diffusion coefficient in this modeling. This parallel diffusion coefficient depends on radial distance, magnetic field, magnetic rigidity, and time. These dependencies are taken from observations.
Yeah, but this really sounds very artificial, that a function is a product of function of separate variables. What is the reason to assume this?
This is the diffusion theory, that we have different dependencies of diffusion coefficient, parallel diffusion coefficient on radial distance, on magnetic field, on energy.
Yes, I understand this, but why this is a product of functions that depend on separate variables?
Maybe because it is quite simple. Yes,
okay.
this is quite simple situation. And in this figure we can see a diffusion coefficient that depends in that way, and we can see that this diffusion coefficient depends in that way. And if we solve our equation, here we can see expected cosmic ray intensity. This is the red one. This is the blue one. This is the expected model. And we compare this intensity with our neutron monitor measurements. And we obtained a quite good correspondence between experiment and model in shape and also in amplitude.
But this agreement is obtained by fixing some parameters.
Yes, by this.
So this is a fit.
Yes,
You fit the parameters in
Yes.
such a way that
Yes.
you get.
We
Yes.
fit parameters.
And how many free parameters do you have in this? model?
Yes, unfortunately a lot. Because the situation is very complicated. This is the simple model. It was a finite difference deterministic method, and next we apply stochastic approach to the Parker transport equation. And in this approach we have independent random processes. Individual particle motion is described as a Markov's process, and this algorithm is easy to parallelize. And significant of is possible significant acceleration of calculations, and so this method is constant time effective. In this approach, we start from Fokker-Planck equation, very famous time forward Fokker-Planck equation and time backward, and we write corresponding stochastic differential equation to this Fokker-Planck equation. And in this equation, dr is the individual pseudo-particle trajectory in the phase space. This is the radial distance, heliolongitude, heliolongitude, and energy. And dw is the Wiener process with randomly fluctuating in Gaussian distribution. Some discussion about the time forward versus time backward integration in this equation. In time forward integration, here we can see a sample of pseudoparticle trajectory in the heliosphere. Here we can see 1, 2, 3, 4 particles. In time forward integration, pseudoparticles are initialized from various points at the boundary of the heliosphere, and after that the trajectories are traced up to the target position. For example, Earth orbit. In this approach, we must have a high number of pseudoparticles in order to obtain enough statistics.
But
And
could you show again the equation? Because I'm curious, where do you get the forces here? That means the values of A and B, where did it come from?
The coefficients are the same as earlier, and B is the matrix. I can show you.
But this matrix, what does it represent?
Yes, this is the matrix which is dependent on these coefficients.
But what is the physics behind it?
In other words, before you write Fokker-Planck equations, you need to have some deterministic thing
Yes.
over which you are able
Yes.
to average.
Yes.
So you are
Yes,
showing
this
us a result of some reasoning, and the question is what is the source
What are
of
the
this?
physical forces
Yes.
that act on
Yes.
this particle?
This is the deterministic coefficient, and this is the matrix which we have for calculations. Maybe I show later the values of matrix B and the coefficients. So the time forward integration is not so very effective for this situation, for this equation, and it is also time and money consuming. In the backward, I skip. Here we have equation, Parker transport equation in 3D space, in heliocentric coordinate system, and this equation is to this equation we write corresponding set of stochastic differential equations. And,
But we still don't know what
this-
B is. Here
yes.
it is.
This is the coefficients which were earlier, and B is the matrix in this form. Is the lower triangular matrix, depending on these coefficients.
Is it possible to derive this B somehow from something?
Yes. Yes. Maybe I skip. In the time backward integration, pseudoparticles are initialized from point of interest, so for example from Earth orbit, and are traced backward in time until they cross the boundary of the heliosphere. In our case, it is 100 astronomical unit. Advantage of this method is that the number of useless particles is reduced. And this backward integration is more efficient for this type of phenomena.
But you told us before that the equation is parabolic, so
Yes?
what does it mean time backward? In parabolic case, you are not allowed to, because the initial value problem in the direction of
You
In
can
the-
see that this is not equivalent because
That's right.
it's easier to do.
There are different.
Therefore, that's the sign of,
The point is that the equations for the backward are different.
yeah.
Yes. And
Yeah, but
This is not
if
just
they-
a time reversal
It's
applied
not
to
as
the
a-
forward
Yes,
equation.
this I understand, but
In
in any
But
case,
the
if the
initial
real
problem-
problem is parabolic, then
Yes.
there is no way to integrate it backward.
It's not the,
it's
it's not the partial differential equations that are
That's right.
propagated backwards, but the trajectories.
Yes.
Yes.
Trajectories
Trajectories. Yeah,
integrate
trajectories obey some
Yes.
irreversible equations.
So in our analysis, we apply time backward integration. A few words about the solution. As a solution, we find the average distribution function, which is this average over different pseudoparticles, and F is the cosmic ray local interstellar spectrum unmodulated. So beyond the heliosphere. And this is the function of kinetic energy in this form. So this is what we want to do. We want to apply different numerical approximation to the solution. So depending on the Ito-Taylor expansion, we use first approximation Euler method, next approximation Milstein method, and the third method is stochastic Runge-Kutta, and the order of convergence is for Euler 0.5, for Milstein 1, and for stochastic Runge-Kutta 1.5. So our trajectory is we can write in this form, and this parameter phi is quite complicated, and using stochastic Runge-Kutta we must apply new random variable dz. This is some technical aspects of our calculations. So for Euler method we obtain trajectory in versus time in radial distance, heliolatitude, heliolongitude, and for energy. And for higher order methods, we obtain trajectory versus radial distance for Euler, Milstein, and stochastic Runge-Kutta, and the similar procedure is done for heliolatitude and heliolongitude. Initial and boundary conditions for this stochastic approach. First, we assume empty heliosphere at the starting point, and we assume also inner reflecting radial boundary at 0.001 AU, and also periodic character of distribution function versus heliolatitude, and heliolongitude. Some details about numerical realization. Numerical realization is done in MATLAB. We use parallel toolbox in MATLAB. We apply time backward integration, and first we shall know the solution at Earth position. So we assume the starting point is. And some results. Here you can see trajectories of pseudoparticles. In this case, we have 2000 pseudoparticles, and here we have radial distance versus time. Here we have heliolatitude versus time, and here we have heliolongitude versus time, and this is for Euler method, this is for Milstein method, and this is for stochastic Runge-Kutta method. You can see that the results are comparable. We can see that for stochastic Runge-Kutta we have a bit longer traveling of cosmic rays, and we have more wide distribution versus heliolongitudes, and more narrow for Euler method, and more narrow for stochastic Runge-Kutta. Here we can see a distribution, latitude versus longitude, latitude versus longitude, and this result also for higher latitudes. Here we can see proton spectra for Euler, Milstein and stochastic Randall-Kruta method, and we can see very good coincidence between them. And we shall study the statistical precision of our analysis, and we calculate standard deviations of this omnidirectional distribution function, and we find that for stochastic Randall-Kruta the standard deviation is very stable and is the lowest, and for Euler method this standard deviation is the highest. And the last part, the last part of my talk is the model of the 27-day variation. As I said previously, 27-day variation is the variation connected with solar rotation. We, in this picture you can see solar wind velocity, points, red points are measurements, and dashed line is this formula. This is the approximation of the experimental data, and we think that the main driver of solar wind of cosmic ray intensity 27-day variation is connected with solar wind velocity, and we apply this formula of solar wind velocity into our equation, and we obtain some results. This is expected cosmic ray intensity modeled by finite difference method and by stochastic differential equations. And points are measurements of cosmic rays by neutron monitors. We can see that we obtain quite good correspondence between modeling results and
Just by
experimental
fitting,
data.
you just fitted the parameters.
Yes.
With
this parameter, solar wind velocity.
So with with 3 parameters, you can certainly fit this curve. Why did you stop at the 3rd parameter? You could put more functions than you could do even
This
better.
one?
Yeah.
This one? Yes, this is no problem. This
So-
is the example of free harmonics in solar wind.
Yeah, but what is surprising here, if you have points, you can always fit a curve.
In other words, there is always with such studies a question of the predictive power of the theory. Yes.
The problem in this investigation is
Because of
what should be the parameters of the interplanetary space, and which could explain observations. This is the.
But this does not explain. Fitting is not
Which sense
explained.
explain, it is not explain.
You fitted a curve so that it would match the observation points. It's not an explanation.
No, but it's a way of measurement of
Yeah.
those coefficients.
It's the way of trying to determine what are the values. That is true. Provided whole machinery is trustful.
And in this figure we can see comparison between Euler, Milstein and stochastic Randall-Kruta methods with observations, and we can see also quite good science. This is our model. So future plans. We shall to study heliospheric parameters from observations. First part is from neutron monitors and meson telescope data. This is continuation of our investigation, and we shall start collaboration using multifractal description of solar wind turbulence
I'm sure this last point would be easily funded.
Yes, I think so. This is very,
Czytam
this is not
z
easy.
gazety.
multi-factor description. And we want to also study relationship, if any, between cosmic ray variation and climate change. This is our Department of Physics and Numerical Analysis, Professor Michaela Wania, Chair, Professor Iskra, it's me, and my colleagues Agnieszka, Anna and Marek. We have also international collaboration with Cosmic Ray and Space Weather Center with Professor Dorman, University of New Mexico Department of Physics and Astronomy, Professor Hadzi Kaluvalia, and the Institute of Solar Terrestrial Physics of Siberian Branch of Gas with Professor Zdobny. So, thank you very much for your attention.
Why neutrons are here being investigated? Because there are also protons.
Yes, it's
Is
a very
this,
good
is this
question.
because it's easier to detect neutrons?
Yes, it's a very good question. In 1950s, when Simpson construct neutron monitor, they measured in atmosphere that the spectrum of neutrons in versus distance from the Earth is very stable. And after that, his
But the reason that there are so many neutron detectors, is this due to the fact that they were introduced because of the nuclear tests and they wanted to monitor nuclear tests?
Yes. The spectrum of neutrons in the atmosphere was very stable versus the radial distance from the from Earth. I think it works very well up to now. This detector.
And these cosmic rays, where do they come from? They come from outside heliosphere, yes?
We call it galactic cosmic rays, but we don't study the sources of cosmic rays. We call it galactic cosmic rays.
But do you know the direction from which they come?
In the heliosphere, we don't see any direction. For us, they are isotropic, more or less. In this interval of energy, they are more or less isotropic.
Okay, so you cannot say like from the galaxy center or from the opposite.
I can't say about it.
More questions or comments? If not, let's thank the speaker.